This is section 4.1, the structure of the atom, early ideas about matter. The objectives of this lesson would be compare and contrast the atomic models of Democritus, Aristotle, and Dalton, and how to understand how Dalton's theory explains the conservation of mass. Some vocabulary review will be theory, and some new vocabulary we'll come across is Dalton's atomic theory. Science as we know it did not exist several thousand years ago. No one knew what a controlled experiment was, and there were few tools for scientific exploration. Although the intellectual thought was there, the curiosity was present, there was just really no way in which someone can go ahead and test them out. Right? Many people believed that at the time that the elements that existed were earth, water, air, and fire. And that these elements could not be divided into smaller and smaller pieces. So, Greek philosopher Democritus was the first person to propose the idea that matter was not infinitely divisible. He believed matter was made up of tiny particles called atoms, which is Greek for indivisible. Democritus believed that atoms could not be created, destroyed, or further divided. While a number of Democritus' ideas do not agree with modern atomic theory, his belief in the existence of atoms was amazingly ahead of his time. However, a lot of people criticized what is it that hold atoms together, and again, Democritus did not have any answers to those questions because the science just was not up to the time. The instruments were just not ready. In comes Aristotle, who is one of Greece's most influential philosophers. He rejected the notion of atoms because it did not agree with his own ideas about nature. One of his major criticisms was the idea that atoms moved through empty space, and he did not believe that empty space could exist. His ideas were one of the most influential of his time, and therefore most people eventually just rejected Democritus' ideas. And again, just to be fair to the people of the time, it was impossible for them to go ahead and know what would hold all these atoms together, as none of these instruments to go ahead and test their experiments or their thoughts, their experiments could not exist. Unfortunately, for the advancement of science, Aristotle was able to go ahead and gain wide acceptance for his ideas of nature, ideas that denied the existence of atoms. In comes the turn of the 19th century, was John Dalton. The work done by the 19th century, John Dalton, who was a English school teacher, marks the beginning of the modern atomic theory. Dalton revised Democritus' ideas based upon results of his own research, and a lot of Dalton's and Democritus' ideas are sort of similar. Thanks to the advancement of science during Democritus' day, Dalton was able to perform experiments that allowed him to refine and support his hypotheses. Dalton studied numerous chemical reactions, making careful observations and measurements along the way. Dalton was able to go ahead and use mass ratios based upon chemical reactions to go ahead and create Dalton's atomic theory. And he proposed this in 1803. Right? So just kind of review, right? Democritus' ideas was that matter is composed of atoms which move through empty space. Atoms are solid, homogeneous, indestructible, and indivisible. Different kinds of atoms have different sizes and shapes. Sizes, shape, and movement of atoms determine the properties of matter. Aristotle said that empty space cannot exist, and that matter is made of earth, fire, air, and water. Dalton, his idea of atomic theory states that matter is composed of extremely small particles, in which we call atoms. Atoms are indivisible and indestructible. Atoms of a given element are identical in size, mass, and chemical properties. Atoms of specific elements are different from those of another element. And different atoms combine in simple whole number ratios to form compounds. And in a chemical reaction, atoms are separated, combined, and rearranged. Right, just to give you an idea, to compare and contrast the periodic table of Dalton's day to ours, in the book New System of Chemical Philosophy, John Dalton presented his symbols of the elements and their possible combinations, right? So if you kind of take a look, right, all of these would represent different elements, and when elements combined, they form these compounds, right? Much different than the periodic table that we have today, where we use letters to go ahead and represent different elements. And one of also Dalton's experiments is that he was taking elements of A and he was combining them with elements of B, and he was noticing that they were combining in these ratios, and that the elements, when combined, would go ahead and conserve mass, right? Mass is not created nor destroyed, it is only transferred. So A plus B, right, we're creating compounds A and B, right? And depending on how much you had of A and B, that the mass of AB would be the summation of A and B. Right, and we call that the conservation of mass. Right? Mass is conserved in any process, even during a chemical reaction. And Dalton's atomic theory easily explains that the conservation of mass in chemical reactions is the result of the separation, combination, or rearrangement of atoms. Atoms that are not created, destroyed, or divided in the process. So there's no sort of nuclear reactions happening here. The formation of a compound from the combining of elements and the conservation of mass during the process, right, was shown in the figure above. The number of atoms of each type is the same before and after the reaction. So if you're starting with A and you're starting with B, you're just going to go ahead and get some sort of combination or rearrangement of A and B as your product. Dalton's convincing experimental evidence and clear explanation of the composition of compounds and the conservation of mass led to a general acceptance of his atomic theory. This was a huge step toward the current atomic model of matter. However, not all of Dalton's theory was accurate. Often in the case of science, Dalton's theory had to be revised, and additional information was learned that could not be explained by the theory. As you learn later on, Dalton was wrong about atoms being indivisible. Atoms are divisible into several subatomic particles, your protons, neutrons, and electrons. Dalton was also wrong about how atoms of a given element have identical properties, right? And we can see that in the form of isotopes, which leads to atoms of the same element having slightly different masses.